Hi, I'm happy to share our work on LLMs training data beyond verbatim memorization. I'm Zitai Chen, and this is joint work with Reza Shukri. So, large language model can memorize their training data. Some are fully memorized, and most are partially memorized. In this work, we discuss how to extract partially memorized data. As a quick recap, LLMs are fundamentally data-driven. They are trained on enormous corpora, such as web text, code base, medical records, and some of that data is private. That is tolerable under one condition. The data goes into the model and never comes back out. But that condition doesn't hold. Model memorize at training time and reproduce at inference time. When they do, training data is exposed without owner's consent. That is a privacy breach, and it doesn't matter whether the content is sensitive. Any reproduction without consent is a breach. However, shows that the risk of memorization, and the bigger the model, the more it memorizes. Training data extraction is how we measure the risk. Given the model a training prefix and see whether it hands back the training suffix. So how does the literature approach extraction today? Existing extraction nearly all follow the same two-step recipe. Generation, then audit. Prompt the model with a prefix, let it produce a suffix, usually with greedy decoding. Then audit that text with membership inference attack. If it scores high enough, membership inference attack call it a member. Notice what this pipeline is really doing. It generates blindly and only afterward checks whether it got lucky. It doesn't search for the member sequence, it waits for them to turn up. That's wait and see. Design brings in two problems. First, incompleteness. Greedy decoding can only extract what the model memorized verbatim, where the member token ran top 1 at every single step. But that's about 10% of training sequence. For the other 90%, the model still knows almost every token. It just let a more generic token etch out the member token at some precision. Those partially memorized sequences are never generated. Because they are never generated, they never audit. But MIA could identify them without any trouble. The risk is real, it just falls outside the audit. Second, inefficiency. Generation is the bottleneck, but nothing tells it what it is looking for. Decoding optimized for the most probable sequence, not the member sequence. The membership signal arrives only after generation is over. It never gets a chance to steer the generation. Let's take a look at incompleteness first. To fix it, we need to stop treating memorization as yes or no. That's what KN correction gives us. Take the member sequence at each suffix position, ask one question. Does the member token rank top 1 given its member prefix? If a more generic token etch it out, that counts. K is how many times this happened, and N is the suffix length. So when K equal to 0, it is verbatim memorization, and K equal to 1 or 2 means the model knows almost the whole suffix and sleep at 1 or 2 stop. Memorization becomes a spectrum, and K tells you where the sequence sits on it. Look at the example, Alice ID. Greedy gives us 6 at the position 7, so it is wrong and the prefix looks safe. But the member token isn't gone, it sits at rank 2, with high confidence, hidden behind a token that's slightly more generic. Correct one position from 6 to 7, the whole ID comes out. The memorization was there the whole time. Greedy has no way to see it. So what this notion tells us about a model? We apply it to privia across 7 domains of the MIMIA benchmark. First, the distribution of K with a suffix length of 10. Only 10.5% of sequence are fully memorized. Everything else is partially memorized, and the part matter most for us is K equal to 1 and 2. They account for 80.7% of the data. That's nearly one sequence in 5 where the model gets 9 or 8 position right out of 10. And greedy decoding still walk away with nothing. Second, the scale. On the right hand side, average K per domain from smallest model up to 12 billion parameter models. The curve goes down in every domain. Larger model memorize more. That confirms what prior work have reported. Now the inefficiency. Start with a question. How do you recall a number you only half remember? At least I did say. You don't write down all 9 digits and then check at the end. Because if a digit 6 is wrong, you don't just got one digit wrong. Everything after it was recorded in a wrong context. At that point, you are remembering a different number entirely. So, you check as you go and you correct before you continue. That is the shift. Existing extraction generate the whole suffix and then audit once. We audit at every step. Generation then audit becomes audit in between generation. Existing attack already paid for the MIA. Just at the end, when the only thing it can tell you is that you already failed, we spend it where it can still change the outcome. Concretely, membership decoding is greedy decoding with one line changed. Greedy asks, which token is most probable? We ask instead, which token does the target model believe more than it should be? The distinct is the whole method, because probability confuses two things. A token can be likely because it is generic. Any model will say it here, or it can be likely because this model was trained on it. Greedy cannot tell those apart, so the generic token wins. For comparison, we bring in the second opinion, a small reference model to represent how average model will do. For each candidate, we compare the two opinions. If the reference agree with the target, the token is just generic. The ratio is about 1. If the target is confident and the reference have no idea, that gap is the fingerprint of memorization, and that's the member token. Here is the score itself. The member token shows more belief in the target model than in average model. To approximate the belief in average model with only one reference model, we interpolate the belief of a reference model with a constant overconfident belief. Here is the setting. 10 consecutive token, auto-regressive, no ground truth at inference. Each row of K is a different claim. From 0 to 2, the data changed from fully memorized to less memorized by the model. Start with K equal to 7, we got around 87% accuracy. And I want to be direct here, greedy get 100. By definition, these are exactly sequence greedy solved. We lost 30 points because we don't know K in advance, and we don't know where the error is. So we audit at every step, including the step greedy already have the right token. Occasionally the score overrule a correct token, and that's the cost. Here is what it buys. K equal to 1, we extract 9% of sequence. Greedy extract 0. Run wrong turn lose the whole suffix, and no amount of compute fix that in one shot. So this isn't an improvement over greedy. These sequences were outside the reach of one-shot extraction entirely, and now they are not. This is a qualitative breach. For K equal to 2, under 1%, I will call it a proof of existence. The extraction boundary isn't stopped at K equal to 1. 3 things to take away. Verbatim memorization is the tip of the iceberg. KN correction measure the rest and give you a memorization profile. Audit in between which the sequence greedy cannot. Not more of them, but different one. There is a difference and it already deployed it. Restricting the number return token is doing the real protective work. The sequence recoverability drops sharply as the number decreases. That's a level provider already have. Thank you for your attention. We hope you find this presentation informative.